In the 0 1 knapsack problem, we have a knapsack of fixed capacity. We have n items, each with a weight and value. We have to keep items in such a way that the value of the kept items is maximized. Since the knapsack has a fixed weight capacity, the sum of the weights of the kept items must not be greater than the capacity of the knapsack. In this video, we are going to use dynamic programming approach to get the solution of 0 1 knapsack problem. Dynamic programming is a method used to solve problems by breaking them into smaller subproblems, solving each subproblem only once, and storing the results to avoid repeated work. It is especially useful when the problem has overlapping subproblems and optimal substructure. Let's try to understand both the properties. Let's say we have a knapsack with a capacity 6. We have multiple items available, but we achieve the optimal result, or in other words, the maximum total value by including item 1, item 2, and item 3 in the knapsack. The values of items 1, 2, and 3 are x, y, and z, respectively. Therefore, the total value of the knapsack is x plus y plus z. Now we remove item 3 from the knapsack and reduce the knapsack's capacity by the weight of item 3. At this point, the knapsack contains only items 1 and 2, and its value is x plus y. The question now is x plus y the maximum possible value for a knapsack with this reduced weight capacity? Suppose someone argues that at this state, other items could give a higher total value. Let's assume there are items 4 and 5 that together give a total value of x dash plus y dash, which is greater than x plus y. But here's the problem. If we now increase the knapsack's capacity back to 6 and re-add item 3, the new value becomes x dash plus y dash plus z. Since x dash plus y dash is greater than x plus y, this means x dash plus y dash plus z would be greater than x plus y plus z. That contradicts our original claim that x plus y plus z was the optimal solution. In conclusion, we can say any assumption that a better combination exists for the reduced capacity leads to a contradiction, as it would imply that the original solution was not optimal. Therefore, the reduced subproblem also has an optimal solution formed by the remaining items. Now we know that by removing an item from the optimal solution of the original 0 1 knapsack problem and reducing the knapsack's capacity accordingly, the remaining items still form an optimal solution for the reduced problem. Or to say it another way, if someone wants to solve the original problem, they should start by solving the smaller subproblem first. That's because the best solution to the subproblem will help build the best solution for the original problem. This property is known as optimal substructure property that states that a problem has optimal substructure property when the optimal solution of the problem can be obtained by solving the subproblems. We start with an original problem where the knapsack has a weight capacity 6. We break this down into two subproblems. Now, let's look at a subproblem where the knapsack has a capacity of 3. We find the best solution for this subproblem by keeping item 1 and item 2 in the knapsack. This subproblem with capacity 3 is part of both subproblem 1 and subproblem 2. So, the solution for this subproblem might help solve subproblems 1 and 2, which in turn may help to solve the original problem. Since subproblem 3 contributes to both the original problem and subproblems 1 and 2, it's a good idea to save its solution somewhere. So we don't have to calculate it again when solving subproblem 1, subproblem 2, or the original problem. In the same way, we can save the solution for subproblem 2, which may be reused in subproblem 1 or the original problem. We can also save the solution for subproblem 1 since it may be used in the original problem too. The main idea is this: store the solutions of subproblems so we don't have to recalculate them every time. This property is known as overlapping subproblems, which states that when the solutions to subproblems are needed repeatedly, it's better to save them to avoid recalculating each time. Try to understand this with an example. Suppose we have 5 items and a knapsack with capacity 5. In dynamic programming, one of the key ideas is that we store the solutions of subproblem to reuse and we need one storage where we store them. Here we use an array of size 6 cross 6 because number of items are 5 and capacity of knapsack is 5. We call this array value of knapsack in short VOK. Now we start the process. First we consider when there is no item. Here item 0 entry represents no item. Now we make the capacity of knapsack 0. First subproblem is when there is no item and capacity of knapsack is 0. We calculate optimal solution in this case. Obviously, value of knapsack will be 0. But here, we are not going to calculate value. I just want to show that how entries in the array will be done and what we have to keep in the mind to calculate the solution. Now, increase the capacity to 1 and calculate the value. We will increase the capacity of knapsack by 1 unit and calculate the optimal solution of subproblems. Now, we consider the first item and start doing the entry in the array. We repeat the process again starting from when the capacity of knapsack is 0. In the next step, we add item 2 in this problem and do the entry in the table, starting from making the capacity of knapsack to 0. Here, all entries are done in this row is considering that we have two items 1 and 2. Similarly, we will repeat the steps by adding item 3, item 4 and item 5. All entries represents the solution of a unique subproblem. Let us say we are calculating solution of a subproblem where items 1, 2 and 3 are present and capacity of knapsack is 5. In the array we can write we have to calculate the value of VOK 3, 5. This two-dimensional array, each cell represents a subproblem. For example, this first cell represents a subproblem where there is no item and capacity of knapsack is 0. We are solving all subproblems row-wise because solution of small subproblems can be used in relatively larger subproblem. Because 0-1 knapsack problem satisfies both properties, optimal substructure and overlapping subproblems. Let us say we are going to solve the problem where number of items is 3 and the current weight capacity of knapsack is 5. It means we already have solved and stored solutions of subproblems considering no item and all possibilities of capacity of knapsack, one item and all possibilities of capacity of knapsack, two items and all possibilities of capacity of knapsack. These stored solutions can be helpful in solving the current subproblem. So, if in general we write we are solving a subproblem where number of items is I and current capacity of knapsack is W, it means we already have solutions of all subproblems considering I minus 1 items. We will get optimal solution of 0-1 knapsack problem at the last cell where n is total number of items and c is capacity of the knapsack. Now, we need to understand that when we are exploring ith item and there is already I minus 1 items and considering them, we have the optimal solutions of subproblems stored in the array. If current capacity of knapsack is W, we have three possibilities. First, size of item I is greater than the size of current capacity of knapsack. It means we cannot keep item I in the knapsack. Other possibility is when size of item I is less than or equal to current capacity of knapsack. Here we have two possibilities. We can keep it in the knapsack or we can ignore it. We are going to select profitable option among the two. Let us write the expression to calculate the solution for the first case. We have a knapsack and the current weight capacity of the knapsack is 5. Two items with weight 1 have been kept in the knapsack optimally. Consider that we have item I of weight 6 and value 3. We want to calculate the solution of the subproblem where number of items is I and current capacity is W. Before considering the item I, value of the kept items is in the knapsack was this. It means considering I minus 1 items and the current weight capacity W, we already have the optimal solution stored in the array. When we explore item I, we find that size of the item is more than the size of the knapsack and it cannot be kept in the knapsack. Therefore, after exploring the item I, there is no change in the value of the knapsack because there is no change to keep item I in the knapsack. Therefore, we can write this. Now, let's consider the scenario when size of item is less than or equal to current capacity of knapsack. We have a knapsack and the current weight capacity of the knapsack is 5. Two items with weight 1 have been kept in the knapsack optimally. Consider that we have one item I of weight 4 and value 3. Since the weight capacity of knapsack is 5, which is greater than or equal to the size of item, we can either keep the item in the knapsack or we can ignore. Let us see both the cases one by one. If we keep the item in the knapsack, there will be one unit free for other items. We have to find the optimal solution of subproblem where weight capacity of knapsack is 1 and there are I minus 1 items. This expression can be rewritten in general as here W minus weight of I means since we can keep item I in the knapsack, so what is the remaining capacity of the knapsack after keeping item I? The good thing is we already have calculated optimal value of this subproblem and stored in the array. Because we are exploring item I, it means we have already calculated optimal solution of subproblems considering I minus 1 items. Therefore, if we keep item I in the knapsack with weight capacity W, there will be two things that will play a role in the calculation of solution. First, optimal solution for the available space after keeping the item I, and second, value of the item I. This is the possible value of the knapsack when we decide to keep item I in the knapsack. Another possibility is that even when the size of the item is less than or equal to the size of the knapsack, but we decide not to keep the item in the knapsack. In this case, value of the knapsack is the same without item I. This is the solution when we decide to not keep the item in the knapsack. So we have two possibilities. When size of the item is less than or equal to the weight capacity of the knapsack and associated value of knapsack in each possibility is which one are we going to choose? Obviously, the possibility where we get maximum value in the knapsack. Let us summarize all possibilities at one place. We have a knapsack with current weight capacity W. We have an item I. We want to calculate the optimal solution for this problem. There are two possibilities. Size of the item is greater than the current weight capacity of knapsack and size of item is less than or equal to the weight capacity of the knapsack. We consider the first case, value of the knapsack is optimal solution of the subproblem without item I because we cannot keep item in the knapsack. In the second, further, there are two possibilities. One, when we do not keep the item I in the knapsack even when size of item I is less than or equal to current capacity of knapsack. In this case, value of knapsack is optimal solution of the subproblem without item I because we are not keeping item in the knapsack. We select this option if after keeping the item I, value of knapsack reduces. The second option is when we keep the item I in the knapsack. In this case, value of knapsack is value of item I plus optimal solution of subproblem considering I minus 1 items and remaining capacity of knapsack after keeping the item I. Since there are two possibilities when size of item I is less than or equal to current capacity of knapsack, we choose that option which gives more value. So this is the expressions that we need to consider in dynamic programming approach for 0-1 knapsack problem. In the next video, we are going to see a working example where these expressions will be used. Thanks for watching. Don't forget to like, share and subscribe so you never miss what's coming next.